Hello and welcome to this video where I will talk about the concept of terminal velocity. And I'd like us to understand how to describe motion which involves terminal velocity. This is a question which students encounter from time to time in the examination. Maybe you're given an object which is under free fall and at some point it reaches terminal velocity, or you get an object which is moving through a fluid. Let's say you've got a measuring cylinder and you've got a marble at the top. When it is released, after a short while, it achieves terminal velocity. How do you describe that kind of motion using forces? Better still, how can you describe the graph, the velocity time graph of such an object? Now, I want us to consider this situation. You have a measuring cylinder, and in the measuring cylinder, you've got a fluid, a liquid such as glycerin, which is very viscous. And then you've got a marble. Then, when you drop the marble in the glycerin, it's going to accelerate downwards, and then after some time, it will achieve terminal velocity. How does the velocity time graph of that motion look like? And how do you describe that kind of motion using the concept of forces which are acting on the object? We'll start by reviewing one concept which involves velocity time graph, and this is the gradient of a velocity time graph. The gradient of a velocity time graph represents acceleration. Just remember that as we describe this motion. So over here, I'm going to draw such a sketch. Let me just try to draw a simple velocity time graph. This is the y-axis. We've got velocity, and on the x-axis, we've got time. And as soon as the object is dropped into the measuring cylinder, this is how the graph looks like. That's better. And then after some time, at this point, it's going to flatten out. In other words, that line is going to be parallel to the t-axis. Remember, what I have on the y-axis is velocity, and this is, of course, time. Here you've got, let's maybe say 0, and then here you've got a certain velocity, which we are going to call terminal velocity, vt. Let's see what happens to the object as it falls downwards through the liquid. Remember, the measuring cylinder could be a tall one like that. This is the surface of the liquid that you have in the measuring cylinder. And you've got the sphere. You're holding it. You're just about to let it go. Let's see the forces which are acting on it as soon as you let go of the sphere. As soon as you release the sphere, the only force which is acting on it before it enters the liquid is the weight of the sphere. It is its own weight. This is the only force acting on it. Because it's the only force, let's find out the acceleration of that object downwards using F is equal to ma. Remember, when there is a resultant force acting on an object, we can be able to determine the acceleration produced by that resultant force. Let's see. The resultant force on it, this small f here, represents a resultant force. Therefore, it's going to be equal to mg. Remember, the weight of an object is mass times the gravitational field strength. Is going to be equal to ma. And when the m's cancel out, you're going to find that the acceleration of the object is equal to the acceleration due to gravity. It's equals to the acceleration due to gravity. And remember, g, we can take its value to be roughly 10 meters per second squared. So initially, upon release, at that instant when you just release it, the acceleration of that sphere is equal to the acceleration due to gravity. Now, when it enters the liquid, at this point, I'm going to draw it slightly displaced here, there, so that it's different from this. But remember, it's just supposed to be just below here. The weight of the object continues to act on it. W is equals to mg. There is another force which comes into play, and we call it the upthrust, U. There is also another force which comes into play. We call it the viscous drag, D. Viscous drag is the amount of frictional force exerted on this object by the liquid. Upthrust is the amount of force that this liquid exerts on it by virtue of the fact that it is immersed. That upthrust, in a different concept or in a different topic, comes in as a result of the weight of the liquid which is displaced. So let's understand that two more forces have come into play, and this is upthrust and viscous drag. The upthrust of that object, just like the weight of the object, has got a constant value, has got a uniform value, because it is dependent on the volume of the liquid displaced, the value of the gravitational field strength, and the density of that liquid. Those are the factors which determine the magnitude of the upward force which is acting on it. U depends on the density of the liquid through which the object has been immersed, the volume of the liquid displaced, which is equals to the volume of the sphere, which again is constant, and the value of the gravitational field strength, which is constant. Looking at those factors, we can see that the upthrust which is acting on that object is uniform, has got a constant value. Let's look at viscous drag. The viscous drag is dependent on the speed of the object. If the object is not moving, the frictional force on the sphere due to the liquid is zero. But the moment it starts moving through the liquid or through the fluid, then that resistance comes in. It is like when you are running against the wind. You find that the faster you move, the higher the air resistance will be on you. You can view viscous drag as the amount of frictional force which this sphere experiences when it is moving through the liquid. The viscous drag depends on the speed of that object. The higher the speed, the higher the viscous drag. So initially, the speed of the object is almost zero. It is almost zero. So the viscous drag is like very small. But as the sphere falls through the liquid, its speed increases. When its speed increases, the viscous drag is going to increase. So remember that as it falls through that liquid, the viscous drag is going to increase because the speed of the object is increasing. Now let's look at the directions in which these forces act. Initially, W is far much greater than the sum of the upthrust and the viscous drag. Therefore, the object is going to accelerate downwards. Again, when we use this equation, F is equal to ma, let's see what happens to this F. This time, the F will be equal to mg minus the sum of the upthrust and the viscous drag. is equals to ma. I want you to compare this equation here. mg is equal to ma, and mg minus something is equal to ma. And the point which I want you to see is this, that the resultant force acting on the object in this particular situation has reduced. Since the resultant force has reduced, the acceleration must reduce. That is very important. How did the resultant force reduce? It reduced because another force which opposes the motion of the object has come into play. In fact, two of them. One of them is increasing with the speed of the object, the other one is uniform. The point is that both of them are opposing the motion of this object through the liquid. So, when we resolve downwards and we want to get the resultant force, and we resolve in the direction of movement of the object, or at least in the direction in which we feel the resultant force is acting, which is downwards, we realize that mg is greater than the sum of the upward forces, and we have this, and we realize because we have subtracted a force from mg compared to this, the acceleration we get here will be less than g. It's going to be less than g. And then we go to the next point. What does the gradient of a velocity time graph represent? It represents acceleration. And that is why you find that as time goes by, at this point, the gradient is going to reduce compared to the gradient initially. The gradient initially was very high because the graph is very steep, signifying that the acceleration was very high, and it was equal to 10 meters per second squared, which is equal to the acceleration due to gravity. It's almost like free fall. But a short moment after that, the moment these two forces come into play, the acceleration of the object drops. It becomes less than g. And as time goes by, as the object gains more speed, the value of the viscous drag increases. Although this one remains constant, the value of the viscous drag increases, making this factor to increase. And that means that we are continuously subtracting a bigger force from mg as time goes by. What is the result of that? The resultant force becomes smaller and smaller and smaller and smaller. And when the resultant force reduces, the acceleration also reduces. And that is what we see when we look at this graph. You find that the gradient reduces, 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 reduces until the gradient becomes zero. Why has it become zero? Or what is the significance of the gradient being zero? That means that the acceleration is zero. How did it become zero? For acceleration to be zero, it means the resultant force must be zero. That means that at this particular point, at that point, mg is exactly equal to u plus d. They are equal. The sum of the upward forces acting on the sphere is equal to the sum of the downward forces acting on the sphere, which is just mg. I'm going to repeat that because it is very important. At this point, the sum of the upward force, which is upthrust plus viscous drag, is equal to the weight of the object. That means that the resultant force will be zero, because the resultant force is mg minus u plus d, but u plus d is equals to mg. It's just like subtracting mg minus another mg. We're going to get 0 is going to be equal to ma, and because mass cannot be 0, it is the a which will be 0. So the object is going to maintain uniform speed as it moves. And that is how you explain the concept of terminal velocity, or maybe I should have mentioned this, that the velocity with which the object now moves, this object here, is referred to as terminal velocity. That is how you explain the concept of terminal velocity, especially when you are looking at an object which is falling through a liquid. The same can be done with an object which is falling through air. So, but here I'm more concerned with an object which is a small sphere which is falling through a viscous liquid. If you change the viscosity of that liquid, maybe you put in a less viscous liquid, what kind of graph are you going to get? You're definitely going to get a much lower terminal velocity, and the object will reach that terminal velocity much earlier. So if you replace that liquid with a more viscous liquid, this is what we're going to get. It's going to reach terminal velocity earlier, you can see that, and its terminal velocity will be much smaller. In other words, it's going to move more slowly in that new, more viscous liquid. That is how you explain the concept of terminal velocity in liquids.